vary in self-esteem. Different people, and you're probably aware of this as just individuals or even counselors, that people vary in self-esteem or how much they like themselves and feel confident and comfortable with themselves. And let's say we made it nice and easy. We had a 5-point scale in which we were assessing a person's self-esteem. So we'll just put SE for self-esteem here. And we had collected it from 5 individuals. And one person was like a 2.5 on a 5-point scale. One person was like a 1. One person was like a 1.8. Those 2 need some counseling. And then someone had a 4.2, and then someone else had a 4.0. Okay? And so we could actually examine what is the variability in this distribution. So a distribution is just like a set of scores. You could get more technical, but let's keep it simple now. So a mean, which we'll talk about in the future, is just an average. And most of you have probably done this in basic math. And to do that, you just add up your scores. So 8 plus 2 is 10 plus 5 is 15. Carry the 1. And if I make a mistake, please check me and tell me sometimes when I do it. Okay. 3, 4, 5, 9, and 4 is 13. Yep. Okay. So this is sum of x. Okay. So this little thing means sum. It means sum all the scores, add them all up. Okay. X is our variable. Okay. So this is x. Self-esteem is our x. Okay. So the sum of x is 13.5. To get a mean, okay, and a mean equals mean. Okay, for a population, I have a cheat sheet on this that will go up on iTunes U. This little symbol means mean for a population. If it is a sample, it's an X with a bar over it. Equals mean for a sample. Okay. Luckily, the equation is exactly the same, but the mean is equal to the sum of x over n. N is the number of people, or number of data points, or number of points, data points. Okay, and we had 1, 2, 3, 4, 5. Okay, so it's 13.5 divided by 5. Anybody want to give me that? Thank you. 2.7. 2.7. Good, it wasn't too long. Sometimes it's awful. So we have a mean of 2.7. Okay. Again, it's a lot of little symbols. All it is an average. So don't get freaked out if you're one of those math people. Just you're adding them all up and you're dividing by how many there were. Okay, and that is a mean. We'll talk more about means in chapter 5, I believe it is. Okay. So one thing is you could ask about this group of numbers. Well, what is the range? Well, the range is the high score. Range is the high score, which was a 4.2, minus the low score, which was a 1.0. Okay, so there was a range of 3.2. Now that kind of gives you a good estimate of the spread. But real quick, let me show you 2 other distributions that would also maybe have a range of 3.2. No, 4.2. Okay. This distribution would also have a range of 3.2. But notice there's not as much variability. Other than the high score and the low score, all the other scores are the same. And so the range really doesn't tell you much about how much these scores are different from each other, which is what you're really looking at with variability. Okay, so the range sometimes has problems. Also, for example, you could have a distribution like this. Let's say instead of self-esteem, or let's say we're still doing self-esteem. We've got a 5.0, a 5.0, a 5.0, a 5.0, a 5.0. And a 1.8. That's also a range of 3.2. But the distribution looks very different, right? In fact, it's almost like this is an outlier. This is a problem. So when you have extreme scores or outliers or things that don't look quite right, the range won't really demonstrate that. So range can be problematic. And there's some, like I said, there's some other examples in the book of wide range. So then you might say, okay, well, if the idea is how varied these are, different these scores are, well then maybe we do something like difference from the mean. How far away are all of these scores from the mean? And that's called a deviation score. So you could take each value and you could subtract it from the mean, okay? And so you could go 2.5 minus 2.7. So we could have the mean here. That's 2.7, right? Just to remind us to make life easier if you want. And we could go minus, 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 which would give us score minus the mean. Well, 2.5 minus 2.7 is negative 0.2, right? I think, right?
Yes.
1 minus 2.7 is a negative 1.7? Am I doing that right? 1.8 minus 2.7 is?
Negative 0.9.
Thank you. 4.2 minus 2.7 is 1.5?
Yes.
Thank you. And 4.0 minus 2.7 is 1.3. Right? Okay, so you have these difference or distance away from the mean, okay? But then we want to average this to get a single number that shows variability. So if we do the sum of the distance from the mean, what do we come up with? Oh, we did something wrong here. Who's got their calculator? Did I do something wrong here?
I think so.
Where did you have 5 points?
Adding those up.
Yeah, that's not right. No, that might be right. Okay, so negative 1.7 plus negative 1.1 is negative 2.8, and this is 2.8. Oh, it is correct. Okay. So if you add those up together, you get a 0. It doesn't matter what scores you do. Any distribution, if you do the deviation score or the distance from the mean, and then you add up the distance from the mean, you always come up with 0. So this is a problem. Deviation scores don't give you any information about how far away they are from the mean or how clumped together they are, okay? Which is why they go to something called sum of squares. They take the deviation scores and they square them. So now we're going to take each of these values and square it. And luckily I know some of these. So negative, well, I better get my calculator. I know that's 0.04?
Yes.
Oh, thank you. Graham's my mathematician, yay. 0.04. Can you do 1.7 squared for me, someone? That one I don't know. This one's going to be
2.89.
2.89, okay. So if we square 0.9, negative 0.9, we're going to get positive 0.81. If we square 1.5, we're going to get 2.25, and 13 squared I think is 169, 1.69, okay. And now we can add up the deviation scores. Okay, so these are the deviation scores squared, and we can sum those, and we get a full number. Anybody got their calculator? Adriana, you did that for me. 14, 19, 28.
0.79. I'm making this one.
10, 20. Someone check my math. 2, 4, 6, 7. Someone check my math? Who's got their calculator?
I'm working on it.
13, 14, 19.
26 did. I got the same thing.
Okay, so
Yeah, I know.
okay. So sum of squares equals 7.68. You still see me?
Yeah.
Good. That's good. Okay. So we just figured out sum of squares, and it's always going to be a whole number. Okay. The problem with sum of squares, it is used in some differential statistics. However, it's very inflated because everything has been squared, right? And so the value is not within the realm of the measure that we had. It was a 5-point self-esteem scale. But our variability score is 7.68. So it doesn't make like really good logical sense. It's hard for us to understand, well, what does that mean? But it's because of this inflation with the squaring, okay? So let's average average, and it also is because we've added up 5 of them, right? So if you think of, let's figure out an average distance from the mean, you could take sum of squares and divide it by n. And this would be, this is called a standard, oops, no, sorry, variance. Okay. So, this thing is variance when you have a population. Let me write that all the way up. Variance. Okay, if you only have a sample, you use the S squared, and that is called variance as well. So I'll do it both ways. If we have the whole population, if the 5 people is everybody in my population that I'm interested, this is the equation I would use. If it's only a sample, I would divide it by n minus 1, which is called degrees of freedom. But you could just remember n minus 1. So here's population. Trust me, I have a cheat sheet. You don't have to memorize these, by the way. You have to be able to do them, but I will be giving you equations for exams. So this is sample. Okay, so now we're kind of getting an average, and if you remember, sum of squares was the distance sum of the distance from the mean squared. Okay, we're averaging it now. This is going to equal 7.68 divided by 5. What was that? 1.536. Okay, now let's do it if it was just a population. 7.68 over 4.
1.92.
Sorry, if it was just a sample, yes, thank you. 1.92. Okay. So this is variance. We did sum of squares. Then we kind of averaged our sum of squares, and that is variance. Okay. And again, even though this looks more in line with our 5-point scale, it is actually still inflated because we squared things. So what a standard deviation does, in essence, is it unsquares things by rooting them. Okay? So this equals the standard deviation for a population. Population. This is sample here. Sample. Standard deviation. Okay. So now all we're going to do is we're going to do a standard deviation equals the root of the variance. So you take that last number that was in your calculator, someone would take that and root it. Awesome. Okay, so if it had been a population, the standard deviation is 1.239. If it had been a sample, and now we're going to root the sample variance, so we're going to root 1.92.
1.3.
Okay, and so these standard deviations, in essence, are basically the average distance from the mean. But we've had to square it at the beginning and then unsquare it because of the process by which, if we didn't square it, it always sums to 0. Does that kind of make sense? Maybe, maybe not. So mathematically, I don't have time to do this again today, but I will be doing this again one more time before you have to do it. But chapter 2, they cover it in chapter 2, so I wanted to make sure I covered it now. And you can turn me off.